In the last lecture, Peter was, well, we spent a lot of time talking about solid analytic rings. And in the last lecture, Peter started to introduce different kinds of classes of analytic rings, which also work in the Archimedean context. So that's these liquid and these gaseous analytic rings. What I want to do today is I want to talk about some generalities on analytic rings. Partially in service of the story Peter is telling, and partially because it sort of should be done at some point. It's going to turn out when discussing these new examples of analytic rings, it's kind of nice to have a good handle on the category of analytic rings and how to manipulate in it. So I'll just be presenting some various facts about analytic rings and their category. So let me just start with let me start by recalling the definition. So an analytic ring is a pair where this triangle ring is a condensed ring, commutative, say. And mod R inside mod R triangle, meaning condensed R modules, is a full subcategory closed under limits, colimits, and extensions. And such that additionally, if you have any x to I group in R triangle modules from anything in R triangle to anything in mod R, it still lies in mod R for all I. And finally, you demand that the unit object, the underlying ring itself, should lie in this full subcategory. Let's call that last condition star. So now I'll make another definition. So let's say, I don't know, a non-complete analytic ring. It's not a special kind of analytic ring. It's something more general than an analytic ring, so maybe a pre-analytic ring. Is a pair as above, except we don't require star. So it's the concept you get by taking the definition of analytic ring and removing this last condition that the unit object should be complete. So what's the reason for considering this relaxation? It kind of plays a technical role. Because, for example, if you want to produce an analytic ring structure on an interesting condensed ring, then a priori you have to control some X groups in the category of R triangle modules. And that can be quite complicated to do because you would have to understand the homological, a priori you'd have to understand the homological algebra of condensed R triangle modules before you can get going on such calculations. And if this is, for example, some liquid base ring, some convergent Laurent series, it can be kind of difficult to do that. But what often turns out in practice is that there's a simpler ring that you can map to R triangle. In the case of the arithmetic Laurent series, it would just be, say, polynomials and T inverse, such that it is easier to produce a pre-analytic ring structure on that simpler R triangle. And then you have that this condition is not necessarily satisfied. But what I'm about to discuss is that there's a completion procedure that lets you go from any non-complete analytic ring to a complete analytic ring. And that's kind of the most convenient way to do things. And we've also seen examples when discussing adic spaces. So recall with this solid RR plus theory, when we were specifying the category attached to a rational open, we took the category of R modules and then we just specified a bunch of conditions, which actually made it into a pre-analytic ring in this sense. But then this condition was not necessarily satisfied, so you would need to change the R triangle to basically almost the value of Huber's structure sheaf on that rational open in order to get an honest analytic ring. So these kinds of things arise in practice, and in general what you want to do with them is you want to complete them to get something that is an analytic ring in the honest sense. And that's the procedure I want to discuss right now. And similarly, so a map, so
which part is the star?
Just the last parts, yeah.
X is still satisfied.
Yeah, you still require that. That's right. Yeah. Right. So a map of pre-analytic rings. Is just like for a map of analytic rings, it's a map of underlying condensed rings, such that n in mod S implies that, well, the restriction of scalars of n, which is a priori just an R triangle module, actually lands in mod R, and this is maybe better thought of as saying that the base change functor, and then there's the completion functor, the R completion, going to mod R. And then you have the S completion going to mod S. So this completion functor exhibiting this as a localization of this, and similarly here. And this condition here is the same thing as saying if you go here and then you complete, that actually factors through here. Necessarily uniquely, because this is a localization. So it's saying that if you have a map here which goes to an isomorphism here, then it goes to an isomorphism here. So then you get a symmetric monoidal base change functor from mod R to RS. Mod R to mod S, sorry. Okay. So that defines the category of pre-analytic rings. And there's so in other words, there's a fully faithful inclusion. Some category of pre-analytic rings into the category of analytic rings. Oh, so analytic rings into the category of pre-analytic rings. And this inclusion has, and the claim or proposition, this inclusion has a left adjoint. Moreover, so the left adjoint sends, so given a pre-analytic ring, R triangle mod R, this left adjoint, sends our triangle mod R to, and some explanation will be required, but so we take our triangle and we complete it with respect to this, this pre-analytic ring structure here. So we apply the left adjoint to the inclusion from mod R into mod R triangle, and then we take, so to speak, the same mod R. So let me give the proof. So first we need to make sure that this is of the appropriate type. I mean, I need to explain how mod R is actually a full subcategory of mod R triangle hat in order for this to parse as a claim. And then I need to check that this setup satisfies the same axioms as this setup, so it actually defines a pre-analytic ring. So first of all, I should also explain why this is a commutative, a condensed commutative ring. So, I'm sorry? Mod R is the same, yeah. So first of all, so this R triangle hat, so is a commutative ring, condensed ring. So this is a sort of a completely general phenomenon. So we have this mod R triangle and this localization functor to mod R, this completion functor, this R completion, and this is symmetric monoidal and colimit preserving, and it has a right adjoint, which is the inclusion in this case. But when you have a symmetric monoidal functor with a right adjoint, then the right adjoint is automatically lax symmetric monoidal. And in particular, if you take the unit object here, and then you apply the right adjoint, it gets a commutative algebra structure. So is a commutative algebra. In this category, in this tensor category, and therefore a fortiori in condensed abelian groups, so it's a condensed commutative ring. So two, we should check that, and moreover, yeah, so not only, also in this general situation with the right adjoint to a symmetric monoidal functor, if you take any object here and apply that right adjoint, it gets the canonical structure of a module over this commutative algebra. Again, just purely formally. So there's this natural factoring. So we have mod R including into mod R triangle. This actually factors through our triangle hat modules, and then the forgetful functor. And the next thing I should check is that this is actually fully faithful. So that we can indeed view mod R not just as a full subcategory of mod R triangle, but of mod R complete, R triangle complete. And so for that, so the proof is that you can just ask for HOMs. So if you take M and N in mod R, you want to compare HOM R HOM R triangle Mn to HOM R triangle hat m, n. So n is an r hat triangle module. So therefore, this one is the same thing as, oh, I'm sorry. I think I should give myself a little bit more room. So this is the same thing as Hom r triangle hat from r triangle hat tensor over r hat m to n. But now, since n is complete, since n lies in mod r, we can complete this. We can apply the completion functor to this too, and we'll get the same thing. So this is the same as Hom r triangle hat tensor r triangle m hat to n. And now we can use that the completion functor is symmetric monoidal so that we can move it inside this whole relative tensor product. And when you move it in the relative tensor product and use that completion is idempotent, you find that this is indeed just Hom r hat triangle m to n. Okay? So now we have to verify all of the axioms. And this is actually a little bit more subtle because we need to make sure that the x calculations are going to work out correctly. And this argument, so remark, this argument for fully faithfulness will also work for x provided that that the derived completion, so now I don't know what derived completion on R triangle is the same as the completion on R triangle. So recall that we had this notion of the derived category of an analytic ring, which was a full subcategory of the derived category of R triangle, and we had the derived completion functor, which was not necessarily on something sitting in degree 0 does not necessarily agree with the usual completion. It's something whose pi 0 or h 0 is the same as this, but it could have higher homology. For example, in this situation with these weird non-sheafy adic spaces. But in general, we don't have that. So what we can see, what we can formally see is that everything works if we replace our triangle hat by our triangle hat, the derived thing, and use the notion of derived analytic ring. Meaning that if you ask not to give an analytic ring structure on this ordinary ring, but an analytic ring structure on this derived enhancement, then using the same kind of formal argument, you'll be able to check all of these properties. So limits and colimits are actually automatic, given that mod R has those closure properties. But to be closed under extensions in here is more, a priori, more than being closed under extensions here. But if you can make the ext calculations, you'll see that it's the same. And then this is also a question of an ext calculation. So if you were to use a notion of derived analytic ring, then you'd be done with that it wouldn't prove the original proposition because I stated it in the underived way, but it would prove something. So now I think I will introduce a notion of derived analytic ring, kind of in the middle of this proof. So definition. So an analytic E infinity ring is a pair R triangle mod R, or maybe I'll say D of R, where actually it's sort of more convenient to only specify the part that's homologically in homological degrees greater than or equal to 0. So where R triangle is a condensed E infinity ring, and connective, thanks, yeah. So meaning it also only lives in homological degrees. And D greater than or equal to 0 are subset, D greater than or equal to 0 R triangle is a full subcategory such that, so it's closed under limits, co-limits, and such that the internal Hom in our triangle from anything in D greater than or equal to 0, I should say in D greater than or equal to 0 R triangle, to anything in D greater than or equal to 0 R is still in D greater than or equal to 0 R, this full subcategory. Yeah, that's a good, thank you. Yeah, so let's say a pre-analytic ring. And then I want to explain the relation between this notion of analytic ring and this sort of derived notion of analytic ring, and then the bare bones notion on the abelian level that we defined earlier. So the proposition is that so for any connective condensed E infinity ring, our triangle, there exists a bijection between the set of pre-analytic ring structures on our triangle and the pre-analytic ring structures so this is in the old sense. This is in the new sense on just the condensed commutative ring, which is gotten by taking pi 0. And also, analytic matches up with analytic, so, or complete. So I could also remove the pre from both sides. So this bijection on the level of pre-analytic ring structures restricts to a bijection on the level of analytic ring structures. And what is this gotten by? So here you have this D greater than or equal to 0 R is the data. And you send that to just those things in D greater than or equal to 0 R, which happen to lie in the heart. So, well, let's say D equals 0 R triangle, which is the same thing as D equals 0 pi naught R triangle. So when you have a module concentrated in degree 0 over some derived ring, that's just the same thing as giving a module, usual module over the pi 0. So, and in this direction, it's given by sending mod r to the set of those m in d greater than or equal to 0 r, such that HIM is in mod r for all I greater than or equal to 0. So
Does this definition holds that be a problem that d greater than 0 might not be closed on the limit?
limits? Didn't I ask it to be?
No, I mean the whole category does not.
I don't. Can you repeat your question?
Is it perhaps there are lim 1 that goes to like d greater than minus 1?
Lim means R ring here.
Yeah, I mean R.
Yeah, but I still have. Oh, but we gave the argument fixing that. So when you have this assumption, you can see that that holds. If you take an arbitrary direct sum of copies of the unit, then you'll see that products of a fixed, even higher derived products of a fixed, given fixed element will be still in the category. And then if you have an arbitrary product, then you can write it as a retract of a product with a fixed element by taking the direct sum of all the elements. And, yeah, so we did this argument in one of the lectures. Yeah.
I guess he asked if ring is in infinity categorical sense.
Oh yes, was that your question, or well, in any case, it means in the infinity categorical sense. So it means R lim implicitly and R colim. Right. So let me make a remark. So in this special case, where R triangle equals pi 0 R triangle, we see that the two definitions are consistent. Meaning, in the case where the notion of rings overlaps, namely where your derived ring is just concentrated in degree 0, so it is a classical ring, the derived definition of what now an analytic ring structure or a pre-analytic ring structure is matches up with the naive definition we gave on the level of abelian categories. So that's the first remark. And the second remark is this finishes proof, the proof of the proposition on completion. Because what we can do is we can just, so there's no obstruction to proving the proposition on completion in the derived setting. And then we get a, but then we can move it down to the abelian setting by going from the analytic ring structure on this derived thing that we produced to the analytic ring structure on its pi 0 just by applying this procedure here.
There's a question in the chat. Are you really requiring that d greater than or equal to 0 is closed under all limits? I think the claim is that you take the limits in d greater than or equal to 0.
Yes, that's right. Yes.
So these are not limits in the big thing.
Yeah. So somehow there's something going on here. So for example, being closed under the loops functor. So that's actually stronger than you might think because, well, what is the loops in this greater than or equal to 0 derived category? It's you shift it down and then you kill the bottom thing. So it's really just like killing the bottom thing up to a shift. And so, well, that kind of goes into the argument here. That's how you can see that an object in there is an object lies in here if and only if each of its homology groups lies in there. And that's one of the key things that goes into this proposition here. Okay.
Although I think this condition doesn't always match out, Dustin. So if you have something that's complete, the right thing that's complete, so the pi 0 is complete. But in the converse direction, I think you might have some higher mod that's some junk that's not complete.
That's not possible, right? Just because of this fact that if you have something derived complete, then each of its homology groups is also complete? Or am I misunderstanding?
Now you're saying that you get a free analytic ring which on the level of pi 0 is already like it's complete. Then you're saying it's already complete, but I don't think there's any reason for that.
But sorry? One more.
Say that then complete analytic ring structures match up, then you seem to say that if you have if R has a property that only is pi 0 is complete, then it's already complete, but I don't think that.
Oh, you're right. You're right. I'm sorry. Yeah, no, you're right. So then let me rather say, thank you, Peter. So let me rather say an analytic ring here goes to an analytic ring there. And the converse is true if your ring is concentrated in degree 0, so in the setting of the remark. Yeah.
I understand the free analytic infinity ring topologically as a dependent loop space of free analytic ring.
Sorry, the sound is not coming through very clearly, so if you could.
No, don't think about it. Oh, okay. Would that mean that you introduce the infinity, but can understand the infinity for analytic ring topologically or not?
Topological ring? I don't.
No, I mean understand infinity topologically, like because in topology when you use infinity space like independent loop space.
I mean, so here's the way I would think about E infinity is it's just there's a general categorical concept, right? If you have a symmetric monoidal category, then you can look at commutative algebra objects in it. And there's an infinity categorical version of that, which implicitly involves things like E infinity operads or something, but really it's, I mean, and then an E infinity algebra over Z will just be a commutative algebra object in the derived category of Z, in that infinity category with the usual derived tensor product. So if you believe in this infinity category mumbo jumbo, you don't need to think about it in being built in terms of topological spaces and operads explicitly. You can kind of just plug into some simple categorical formalism. Okay, so that's the notion of completion. Yeah, maybe, okay, I'm reassessing that. So maybe the good thing to say is that you have an analytic ring over here, gives you an analytic ring over here such that also the, yeah, so analytic ring structures here are the same thing as analytic ring structures here, such that each pi I, not just pi 0, is complete in this category here. So, yeah. Right. So now, I'm not going to prove the proposition. This was proved in one of the older lectures, so you can look there for the argument. And now I want to move on to the next topic, which is colimits in the category of analytic rings. Or maybe I should make another. Well, sorry, maybe I should make another remark. Yeah, so it's important to note that the derived categories can change when you. So if you take an analytic ring structure on pi naught, it gives you an abelian category, but we also argued it gives you a derived category. That derived category is not necessarily going to be the same as the derived category you get on R triangle when you move along this equivalence, because the higher homology in R triangle can make things a little different. So when we're doing this completion on the level of naive analytic rings sitting in degree 0, it's important to note that, so to speak, the derived category is not the correct one. The derived category of this naive completion, so yeah, maybe I'll make a warning. So if R hat triangle mod R is the completion of R triangle mod R, then it's not necessarily true that the derived category of this thing is the same thing as the derived category of this thing. But only if you use derived completion on the left-hand side. So if this ring that you calculate, if you calculate this derived completion and it happens to live in degree 0, then this will be true, and the derived categories will pass along correctly. But if this happens to have higher homology, then you really should be considering a derived analytic ring instead of an ordinary analytic ring. And this was the phenomenon we saw in adic spaces, that for some rational localizations in very exotic contexts, you get a derived structure sheaf, and then you really should, even though you have an underlying ordinary analytic ring by taking pi 0, you really should be considering the derived analytic ring there. Sorry?
How do the X computations differ?
Well, they're X over different rings.
Right. But like,
Yeah.
they're all in the sense that, like, when you complete it, then like you have that condition that X of mod R triangle mod R lives in mod R.
Yeah.
But then, so now it's still the same mod R.
Yeah, it'll live in the same category, but the objects won't be the same. Yeah.
You can have like wildly different things.
Well, wildly, I mean, you can have different things. These are kind of exotic phenomena. I'm not saying, yeah, so I haven't actually investigated really. I mean, because the phenomena, like when this happens, it tends to be fairly exotic. So haven't really seriously tried to do those calculations. Okay. So, all right. So now we have this notion of completion of analytic rings, and this lets us discuss co-limits of analytic rings. So. There's something else that I maybe should have mentioned in connection with this, what I just erased. So this analytic ring structure is on R, corresponding to analytic ring structures on pi 0 of R, which is that maps in the category of analytic rings in the derived sense are the same thing as maps on the level of derived rings, which are maps in the usual sense, in the old sense when you look on the abelian categories there. Right, so colimits in the category of analytic rings. So the procedure is you take the colimit in pre-analytic rings, and then you complete. And formally, this must be how you compute colimits, just because the completion functor was the left adjoint to the inclusion. So what is this colimit in pre-analytic rings? It's actually quite naive. So if you have a diagram, so Ri, R triangle I, mod Ri, I and I, then the colimit is given by taking the colimit of condensed rings And then, so this is a, yeah. Co-limiting condensed commutative rings. Oh, sorry. What? No, sorry. Sorry. The co-limit of R triangle I of mod Ri is the pair co-limit over I, R triangle I, and that's the co-limit in condensed commutative rings. And then you take a certain full subcategory, so-called mod co-limit I in I, Ri, where this is those M in mod co-limit Ri triangle, such that for all I, M lies in mod Ri. Or when you restrict scalars to Ri triangle, rather, then it lies in that category there. So it's just an intersection of a bunch of categories where those categories are just required, and when you restrict scalars, you lie in the corresponding complete thing there. So this is quite it's quite straightforward from the definition of the category of analytic rings to see that this is the way to calculate co-limits. By definition, a map was a map of rings satisfying a certain property. So you certainly want to put the co-limit of the rings here, and then this definition here is just tailored so that you have the correct property there. And checking that this satisfies the axioms of a pre-analytic ring is also not difficult. So, well, certainly closure under limits and colimits is elementary because the forgetful functor that you're using here commutes with limits and colimits. And the closure under the x's is also not so difficult. Yeah. You just check it directly. So let me now take some examples. So filtered colimits in analytic rings. So the claim is that here the completion is unnecessary. So this filtered colimit of Ri triangle mod filtered colimit of Ri is already complete. So what does that mean? That means that you take this, you have to ask whether this ring lies in this category. But lying in that category means for every I, you lie in mod Ri. But from I on in this filtered colimit, you lie in mod Ri by definition. And so from I on, that's a cofinal collection here. So you can calculate this as a filtered colimit of things which satisfy the condition. So it also satisfies the condition. So an example of this we've already seen is that if R is a discrete commutative ring, then solid R is the filtered colimit of solid Ri, I in I, if R is the filtered colimit of the Ri.
Maybe you should say what you mean by this colimit there.
This colimit here? Yeah, this is in the category of analytic rings.
Ah, for solid R. Okay.
Yeah, so or pre-analytic rings. So, Okay. So if you understand filtered colimits, then the next thing you should try to understand is pushouts. So pushouts. So if you have R goes to A goes to B, R goes to A and R goes to B, diagram of analytic rings, then you need to complete the pre-analytic ring, which is A tensor over RB, and then the full subcategory of those M in mod A, triangle, mod A triangle tensor R triangle B triangle, such that as an A module it lies in mod A, and as a B module it lies in mod B. And here it is important to complete, because this thing has no reason to lie in mod A or in mod B. And in fact, so here's a remark, the completion functor here, a priori, involves iterating A completion and B completion.
This is
Alternating.
so limits in one category or infinity category.
Yeah, so I'm doing it in the one category here, but the exact same thing, all the exact same remarks apply in the infinity category. If you know with the notion of derived analytic ring, you just interpret everything as a derived tensor product and use d greater than or equal to 0 instead of mod. It's all, there's no difference in this discussion. Yeah. Okay, so yeah, in general you'd have to take this thing, A complete it as an A triangle module, then B complete that as a B triangle module, then A complete that and B complete that, past a sequential colimit, and that would be the description of the completion functor for this. In practice it's usually not so bad, but that's a priori what you need to do. And we also had examples of this in the solid setting. So example, if we had one of our RR plus settings and then to a rational open and say spliv R, R plus, then we get a new analytic ring. I don't know. Which was the completion of the pre-analytic ring structure on R, where you enforce all of the relations described that your rational open describes. So if it was F1 Fn over G, then you require that G acts invertibly on your modules, and that Fi over G is a solid variable with respect to all of your modules. And then the pushouts, so new analytic ring, I kind of hesitate to call it O of U plus, but okay, I'll do it anyway, maybe. And then if you take O of U, O plus of U, tensor over R plus with some other OV, O plus V, then what you're going to get is the same thing for the intersection of these rational opens. The analytic ring corresponding to the intersection of these rational opens. I guess in the discrete case, R discrete, it literally is just this. So that the notion of pushout in analytic rings is corresponding to intersection of rational opens here. And that just follows from the definition of this here. So yeah, these pushouts are in general kind of the most important construction because they're geometrically what's supposed to correspond to pullbacks. And this business of having to complete them makes for an additional subtlety compared to the usual algebraic geometry. Okay. So, questions about that?
If the procedure becomes easier when you just consider finite coproduct?
No. It's the case of relative tensor products is no easier. The case of absolute tensor products is no easier than the case of relative tensor products. So in fact, I mean, I didn't really need, in this first part, I didn't really need to say filtered. Sifted is enough if you know what sifted means. And then general colimits, just as general colimits can be decomposed into filtered colimits and pushouts, general colimits can also be composed into sifted colimits and coproducts. So, and concretely, the completion functor for this relative tensor product is just the same as the completion functor for the absolute tensor product. It's
Sifted colimit is easy.
Sifted colimit is just as easy as filtered colimit. Yeah, but to...
So the only difficulty is about the finite coproduct.
Exactly. So yeah, A tensor RB is no more difficult than A tensor B. So, okay, now I want to have a little bit of fun. Well, depending on your definition of fun. Right, so Frobenius. So I want to prove the following theorem. So suppose R is an analytic ring. Then the Frobenius map, which goes from R triangle to R triangle modulo P, it's induced by X, goes to X to the P. That's certainly a map of condensed rings, but this is actually a map of analytic rings. From R to, well, R mod P, by which I mean R hat mod P, and then mod R, yeah. So P torsion elements, yeah. So you just induce the analytic ring structure. So a complete module over R mod P is just a module over R triangle mod P, which is complete when viewed as an R triangle module. So you should probably, I mean, you're free to assume R is characteristic P, in which case it's really just a map from R to R. Okay. So what do we need to do to prove such a claim? Well, according to the definition, what we need to do is, so proof, need to see that if, well, let me assume R has characteristic P, so R is an FP algebra, our triangle is an FP algebra. Just to avoid the notation of them modding out by P and all that, we need to see that if M is in mod R, then the Frobenius push forward of M, which lies in M mod R triangle, actually lies in mod R. And this is this is not so obvious how to check. We have these axioms of analytic ring. They're all about categorical closure properties in linear algebra, like limits and colimits and x and so on. They say absolutely nothing about the Frobenius. They give no kind of hint as to why this should be true. However, let me make a remark. There is another perspective. On maps of analytic rings. So first of all, if R triangle mod R, S triangle mod S is a map of analytic rings, then for all light profinite sets, T, we get a map, an R triangle linear map from R bracket T, the free R module on T, to the free S module on T.
So by phi you mean Frob?
I mean Frob, yeah. Frobenius is a map of rings. So, yeah. Thanks. And the reason is, well, by hypothesis of this being a map of analytic rings, what it means is that these modules here are actually live in mod R. That's equivalent to being a map of analytic rings. You need to check it a priori for all S modules, but by colimits, it's enough to check it for a generating class. In fact, so for these guys, in fact, you can even take T to be the Cantor set if you like. So this is the thing that you get, is that this is an R module, so that the map from the free R triangle module on T to it factors through RT. And this is functorial in S. Functorial in T, sorry. Moreover, well, so these aren't quite arbitrary. There's a small extra there's an extra condition that in particular is satisfied by them. So if you do have a map from T to R triangle, so a map of condensed sets from T to R triangle, then there's two things you can do. One, you can make a map from R bracket T to R triangle, an R triangle linear map, because by definition of analytic ring, this thing is complete. So you go to R triangle bracket T, and then you go to R bracket T. But then you also have this map here that we've assumed exists from R bracket T to S bracket T. But on the other hand, you can compose this to S triangle, and you get this thing here. So this is just the map of rings. This is the thing we posited to exist. And this exists for the same reason this exists. And that square will commute when you have a map of analytic rings. So I want to claim this lemma. Conversely, if R triangle to S triangle is a map of condensed rings, such that there exist these maps from RT to ST satisfying the conditions above, then R to S is a map R to S. So this is nice because you don't have to explicitly think about how you'd build S bracket T from R bracket T modules. If you just have the maps that would kind of indicate it, then you can actually do it. Let me maybe give a hint of the argument. It's in the notes from a previous iteration of this. So a hint of the argument would be that. So note that. Well, would be to note that. So a hint of the argument is that mod R is monadic over condensed sets. So you have a forgetful functor from mod R to mod R triangle, which in turn forgets to condensed sets. And that satisfies the hypotheses of Barbeck. It's basically a localization, or the right adjoint of a localization followed by a forgetful functor. And so this category can be understood as the category of whatever they call it, algebras over some monad here, which is kind of the free R module monad. And then if you want to show that every S module is an R module, it would be enough to produce a map of monads from the free R module monad to the free S module monad. Well, the very first step in producing such a map of monads would be giving the map from the free object here to the map of the free object here. And then there's a condition you need to check, compatibility with the monad structure. And if you play around enough, you can reduce what you need to check to just this commutative diagram here. Okay? All right. So let's continue discussing Frobenius. So now, what are we reduced to? So we need to, for every light profinite set, T, a map, a Frobenius linear map from R bracket T to R bracket T, satisfying, well, it should be functorial in T, and it should satisfy this little extra condition relating to when you take a map from T to R. Okay? So now let me recall, just in pure algebra, a little bit about the Frobenius. So recollection on Frobenius. So Frobenius is a map of rings. So I said it's a map of rings from R to R mod P. But actually, in some form, it exists for an arbitrary abelian group. So if M is an abelian group, then you get a natural map from M to, well, the zeroth Tate cohomology of CP acting on M tensor P. So P is a prime. So recall that this is the co-kernel of the norm map, or the transfer map maybe is a better name for it, from M tensor P CP orbits to M tensor P CP fixed points.
Maybe say that CP is a specific group of order P.
Yes, thank you, yes. And I'm going to, this is quite long notation. I'm going to adopt some homotopy theory abbreviation for this. I'll just write pi 0 of the CP of the Tate cohomology written in the style of homotopy theorists because it's shorter. So, and what is this map induced by? You send an element M to the diagonal tensor, M tensor M P times, which lives in M tensor P, and it's clearly fixed by the cyclic group of order P, and then you take its class in the Tate cohomology. Okay? And the point is that, of course, this expression by itself is not additive, but if you look at where m plus n goes, you'll have a bunch of cross terms, and you'll be able to recognize that each of those cross terms is a norm from M tensor P. So it's a nice exercise if you've never done it. Sorry. I should continue over here. So I should say it's a group homomorphism. That's the special thing that happens here. And what is the relation of this construction with the Frobenius on a ring? So if M equals R is a commutative ring, then you have this thing, which goes from R to R tensor P Tate CP, and pi 0 of that. But then you can use the multiplication map from R tensor P to R to go to this, where now the CP action is trivial. Here you're using that the ring is commutative, so that it's a CP equivariant map. Multiplication is a CP equivariant map from R tensor P to R. But now since the CP action is trivial, this is just the same thing as this is doing nothing, and then the norm map is just, usually it's summing over the action of the group, but the group is trivial, so you're just summing over P copies of 1. So this really is just R mod P. And if you trace through, this is the Frobenius, so just by the same formula. So okay. And now if M is an R module, then this map, this so-called Frobenius map from Tate CP, this is a map of abelian groups. So these are both R modules. But this is a map of abelian groups, not a map of R modules, but in fact it is a map of R modules if you Frobenius twist the phi twist on the right-hand side. So in other words, this abelian group level Frobenius is kind of linear over the ring level Frobenius in the appropriate sense. So what this suggests is, so now we're trying to look for some linear algebra incarnation of Frobenius on the level of these light profinite sets. This suggests that we should just try to apply this abelian group version of Frobenius and see what happens. So now we take T, a light profinite set. Then we get R bracket T, and we can always do this in, so now we're viewing R bracket T as just a sheaf of abelian groups on light profinite sets, and we can apply this construction here. So we tensor it P times, and we get Tate CP, and then we take pi 0. So that's all just happening at the level of sheaves of abelian groups. So that's a very uncompleted tensor product, but we can always map this to any further completion we like, and in particular we can map it to pi 0 R bracket T. I apologize, this is not the polynomial ring on one variable. This is the free R module on a profinite set T to tensor over R P, Tate CP. But you have this sort of, so to speak, Kuhneth formula. So the tensor products of the free modules are just the free modules on the products. And then the CP is acting here as well, Tate CP. And we wanted to make a map from RT to itself, which is Frobenius linear. And we've gotten to RT to the P, so how do we compare them? Well, we can put RT maps here via the diagonal embedding. And that's also equivariant for the CP action if you make CP act trivially here. So you get a map like this. And the claim is that this map is an isomorphism. If you buy that, then you're basically done. So, because again, CP is acting trivially here, so the Tate construction is just modding out by P. So this is indeed R mod P bracket T. And then for similar reasons, the composite is actually going to be Frobenius linear and gives you the desired construction. You also have to check that condition, but the full argument is in the notes, analytic.pdf. What I want to highlight is what's different here compared to last time this was discussed by Peter in a previous iteration. Last time this had to be added as kind of an axiom on our analytic rings that, well, basically that this argument works, which reduces to this claim being true. But now that we've switched to the light profinite set setting, it's actually, you can just prove it's true for arbitrary R. So that's what I want to explain now. So to finish, we need to show, so the lemma, so let's say if now S, if S is a light profinite set with CP action, then the map R bracket S, the fixed points, the CP fixed points, which is a closed subset of S, hence also a light profinite set, to R bracket S, induces an isomorphism on Tate cohomology. And in particular on Tate cohomology when you pass to pi 0, so just Tate cohomology in degree 0. Okay? So this is going to use some facts about light profinite sets, which Peter mentioned in his first lecture, but haven't sort of, well, they have been used, for example, for this projectivity of this P space, but well, we're going to more directly use them now. So proof is, so the first claim is that R bracket SCP is actually mapping injectively into R bracket S. And the reason is any inclusion of light profinite sets has a retraction. This was a fact that Peter proved in the second lecture of this course. So if you apply it to the inclusion of CP and S, you find there's a retraction. So then if you hit it with any functor, it'll still be injective. So what does this imply? This implies by the long exact sequence in Tate cohomology, this means it suffices to show that if you take R bracket S mod R bracket SCP, that this thing has vanishing Tate construction. And the second claim is that generally, if you have T inside S, then R bracket S mod R bracket T only depends on the locally compact space, locally light profinite space, which is the complement.
S minus T.
Thank you. It's not like group actions where you can choose, yeah. Okay. So that's not a precise claim. So what's the more precise version of the claim? If you have S prime mapping to S, and then you have T including here, and you form the pullback to get T prime, and if this is an isomorphism over S minus T, so you're sort of blowing up T, so to speak, or you're choosing a different compactification of S minus T, then R bracket S prime mod R bracket T prime maps isomorphically to R bracket S mod R bracket T. And this holds because this square here is a pushout in condensed sets. Which is a little, well, it's light condensed sets, let's say. A little exercise you can see using the definition of the Grothendieck topology. Yeah, I wanted to assume it was a pullback. Yeah. So, okay. And then the third thing is that if, let's say, X is a, let's say, sigma compact, totally disconnected, locally compact Hausdorff space, and CP acts with no fixed points, then X is actually isomorphic to some coproduct of CP many copies of Y, where CP is acting by permuting those copies. Sigma compact means countable union of compacts. S prime? You can choose. Yeah, it's any S prime you like, which maps to S by a map which is an isomorphism over this open subset here. So it's just modifying T, making T bigger. Yeah. Okay. By the way, the thing is, if you have a light profinite set and you remove a closed subset, which is also light, then the complement is one of these guys. It's going to be sigma compact because of the lightness, basically. There's a countable system of neighborhoods of any closed subset, and then it's totally disconnected and locally compact Hausdorff. So, what is Y? It exists. There exists a Y such that, also with these properties, such that. So I'm saying the action is free in a very strong sense. Provided the action has no fixed points, then it's free in a very strong sense. It's just literally induced. So the reason is that, so X to X mod CP is a covering map. That just uses locally compact Hausdorff and freeness of the action. But then this will also be sigma compact, locally compact Hausdorff, and totally disconnected. And as Peter explained, there's an easy argument that this implies that it's a disjoint union of countably many light profinite sets. And the, what's that?
Not necessarily the items changing also together.
Oh, I'm sorry. Yeah. Oh, yeah. Right. In the application, they will be light, but yeah, thank you. I forgot. I should have maybe said locally light or something like that. So it's a disjoint, countable disjoint union of profinite sets. And this covering map will have to be trivial over each of these profinite sets because the topology is totally disconnected, so locally trivial implies globally trivial. And then that implies this because the y's, or yeah, y will just be x mod CP, and then the trivialization of the cover over each profinite set will give you the required decomposition there. Okay. So if you combine 2 and 3, what do you deduce? You deduce that this R S mod, so you deduce that R, in that setting over there, S mod R CP is actually a direct sum of CP many copies of some guy X, where CP is acting on this set here. Whoops, S. Because by 2, this only depends on the light profinite set, which is the complement. That's one of these guys that here. So then that light profinite, or that locally light profinite set is a disjoint union of CP many copies of some guy, and then you compactify it in a different way by just compactifying Y and then taking the CP many disjoint union copies of that to get a compactification of X, and then use that to calculate the quotient here, and then you'll find that the module is induced. And then an induced module has vanishing Tate cohomology. So yeah. Okay. So this fact that Frobenius is a map of analytic rings, it's not just a cute fact. So I'll make a remark. I don't think I'll go into the details. But this theorem on Frobenius implies that if R triangle mod R, or let's do it in this setting. Derived analytic ring, or pre-analytic ring, and we give our triangle the structure of an animated commutative ring, condensed ring, which gives new functors derived symmetric powers on d greater than or equal to 0 R triangle, which are the things that are used to build free animated rings, or you say used to build the monad, describing animated rings over R triangle. Then these sim I descend to, so if M mapping to N goes to an isomorphism in D greater than or equal to R, D greater than or equal to 0 R, so this is a map in D greater than or equal to 0 R triangle, then so does sim I. Which lets you define the sim i's on the derived category of this analytic ring. So this, the argument for this can also be found in analytic.pdf. For this deduction from the statement about Frobenius to the statement about symmetric powers, it comes from a calculation of what Dolden-Pupi did about these so-called stable derived functors of the symmetric power functors. And what does this let you do? This lets you do normalization or completion of pre-analytic rings. Also in the animated context. So you get a good category of animated analytic rings. So this is a pair consisting of an animated commutative condensed ring, light condensed ring, and then a D greater than or equal to 0 R. This is an analytic ring structure on the underlying E-infinity ring, say. Or you could just specify the pi naught level thing or whatever you want. So the extra structure you're putting on here is just that this gets an animated structure. And then the whole discussion works just fine there. Okay. So next, so one last topic. So maybe I'll call it a killing algebras. Killing algebra objects. So recall from motivation that we presented the solid Z theory as the analytic ring structure on the integers, where M was in solid Z, if and only if, when you take internal Hom from P to M, and then you apply this shift -1 to internal Hom from P to M, this should be an isomorphism. But this is equivalent to saying that, say, R Hom from A to M equals 0, where A is equal to P modulo T minus 1. A priori, I should say derived modulo T minus 1, but actually it's easy to see that multiplication by T minus 1 is injective. And in fact, it's not going to matter either way. As in the class of modules satisfying this doesn't really change. So it's the things that, and this has an algebra structure. In the ambient category, say d greater than dz, condensed. Because P itself was a commutative ring object via addition on natural numbers, and then we're just modding out by an element of that ring, t minus 1. Okay. I'm sorry? Goes to isomorphism. I'm sorry, yeah. So if this is a map which goes to an isomorphism in there, then its symmetric power also goes to an isomorphism there. That's the condition you need to extend this symmetric power functor from this thing to that localization of it, d greater than or equal to 0 r.
What would you mean by goes to? You mean take the completion out of it?
Yeah, exactly. Yeah, goes to under the localization functor. Yeah. So general context. So maybe I should say, yeah, so general context. So let's say a C tensor is a symmetric monoidal, let's say presentable, stable infinity category. And yeah, presentable, let me include that tensor product commutes with colimits in each variable. And let's say A and C is an algebra object. And I only need it in some kind of weak sense. So let's say that we have a multiplication map, literally just A tensor A goes to A. We have a unit, so there's the unit object in the symmetric monoidal category, and then we require that the multiplication is either left or right unidal. So let's say so unit tensor A, and then multiplication. This is isomorphism.
So you said that you don't require any associativity or...
No, nothing, yeah. Yeah, it's really, really weak. Okay, then we can define, so D subset C to be the full subcategory of those M in C such that internal Hom, which implicitly is an R Hom here, from A to M equals 0. So we're killing A. We're declaring that A should be equal to 0, but also in an internal Hom sense. And then the goal will be in favorable situations, give a formula for the left adjoint to the inclusion.
Sorry, is killing the name of the mathematician or just kill?
Killing? Killing means not the mathematician responsible for the killing.
I suspect that this kind of things was... yeah.
Probably he didn't do it, yeah. Yeah. Okay. So maybe I should give some examples. Well, there was the solid example that I just described. So there was also solid ZT, which was also obtained by killing some endomorphism of, or requiring some endomorphism of P to go to an isomorphism. But that endomorphism of P was also just given by multiplication by some element with respect to the ring structure on P. So it's the same thing as killing the cofiber, just like this. There's also kind of pure algebra examples. So for example, if you're in usual derived category D of R, and then you look at R mod F, so that's C equals D of R. Then what is D? Well, D is D of R1 over F. So it's kind of inverting F in some algebraic sense is an example of this. Another thing you could do is C equals D of R. Then you could take this algebra instead, R bracket F inverse, and D of R. Then what is D? D is the sort of like F complete derived subcategory. And we're looking for a formula for the derived F completion. Okay. So, right. So let's so define a functor f from C to C by the following. So f of x is internal Hom from so let me write let me write C for the fiber of the unit mapping to A. And then I'll define this functor f by f of x is internal Hom from C to x. And there's a natural transformation from x to f of x, because this is the same thing as internal Hom from 1 to x. And by construction, C maps to 1, so you get a map in the other way on the internal Hom. So I want to claim that this is a first step towards constructing the required localization. So claim if M is in D, then Hom to M applied to this map is an isomorphism. So Homing to M, living in D, doesn't see the difference between x and f of x. Okay. So for the proof, so it suffices to see that the fiber of x maps to f of x is an A module. The reason for that is to show that Homing out of this, from this map to M being an isomorphism, that's the same thing as saying that Homs from the fiber to M should be 0. But by definition, internal Homs from anything in A to M is 0. Therefore, so if it's an A module, then it's actually a unidal. Yeah, maybe I should say it's a retract of A tensor itself. So any A module is a retract of itself tensor A just by the unitality axiom. And then because internal Homs from A to M are 0, that implies that Homs, any kind of Homs from A tensor anything to M is 0. And then you get the same for any retract. And therefore, you get the required claim. So now why is this fiber an A module? But this fiber is just, up to shift maybe, it is just internal Hom from A to X, because A is the difference between 1 and C. So up to a shift, the fiber will be internal Hom from A to X. And this has an A module structure because you can, so to speak, act by A here. Okay. Okay. So now iterate F in the following way. So you get X going to F of X, and then you'll go to F of X. And one should actually potentially be a bit careful about which map one writes down here. So what I want to do is I want to take F applied to the previous map, as opposed to taking the instance of the previous map with X replaced by F of X. Okay. And then you can continue on like this, F of X. And then I claim that, so define F infinity to be the colimit of this here. Then I claim that, I'll do it over here. So claim, so if either this colimit stabilizes for all x. So if, for example, every map from here onward is an isomorphism, or 2, internal Hom out of A as a functor from C to C commutes with colimits, or really maybe only needs sequential colimits. Then X goes to F infinity X is the left adjoint to the inclusion D inside C. So for the proof, you have to check 2 things. One, you have to check that if you map from X to anything in D, that's the same thing as mapping from F infinity X to anything in D. But we just proved that claim for X going to F of X. And this thing is given by hitting an instance of that map with the functor F. But the functor F is going to preserve the property used in the proof here, that the fiber is an A module, because internal Hom to an A module will still be an A module. So the exact same argument shows that each of these maps also satisfies the same property, that internal Homming out of them doesn't see the difference between one guy and the next. And then you have a co-limit, and internal Homming out of that is just an inverse limit of internal Homming out of all the other ones, or Homming, I should just say. So that formally just passes through to the co-limit. So just as for X goes to F of X, each F to the N going to F n plus 1 X is iso on Homming out to D, and then so is X goes to F infinity X. And then the next thing you need to show is that this guy actually, it lies in D. So that's And the second thing you need to show is that f infinity x lies in D. But to check that, you need to check that, by definition of D, you need to check that internal Hamming out of A into f of x gives you the same thing. But by construction, internal Hamming just shifts you one along in the sequence. And so the colimit is going to be the same. So by construction. Okay. So in principle, for example, you could at least attempt to use this formula to compute solidification. It's all actually quite explicit. In that case, this Hamming out of C is just yeah.
I think last thing. I mean, Hamming out of A is not the same as applying to contour M.
Oh. Wait, what? There's two things I skipped here. Sorry. The first thing I skipped was pulling the colimit in, and that's where I would use hypothesis 1 or 2 to be able to pull the Hamming from A into there into the colimit. And then the second thing, as Peter says, I got the wrong explanation. So yeah. So you have to be wait, now I'm blanking. Can you help me, Peter?
I think the argument should be that so you want to know that Hamming A becomes 0, and the argument should be that all the transition maps just become a 0 map.
Ah, right, okay. Yeah, okay. Right, okay, sorry.
I thought I was actually using there was a question which map to use after the first step, and I actually want to use the other map.
Okay, well when I prepared this, I wanted to use this map.
Because I did want to argue that whenever you apply internal Hamming from A to the map from x to f of x, it just becomes a 0 map, and you can apply the same instances.
Yeah. Internal Hamming from A. Yes, but you can use this. I mean, but that also works here because the internal Hamming from A to x commutes with the operation of forming f, like applying f. So
Yes, both are valid for.
yeah, both. Okay. Okay. Yeah. So sorry. Let me try. So for this, you check that internal Hamming A to each fn plus 1 is homotopic to the 0 map. Okay. Yeah, I'm sorry, I kind of. Okay. Right, so yeah, so in the case of solid, you can really just make this completely explicit, and this operation f of x is some quotient of null sequences in x modulo null sequences in x via some map. And it's basically, this f of x is basically you look at all null sequences and you mod out by the relations that would say that intuitively you want to map that to M by summing them, and what you're modding out by is just the telescoping sums. And so you can kind of try to analyze what happens to that and iterating it and so on to get an expression for the solidification of a general module. It's also fun to try to unwind it in these cases and see that you recover the classical formulas. So like, for example, so here well, of course, it's m1 over f, but you can rewrite that as there's this well-known, as a sequential colimit, right? And so I claim that that's exactly the same as this sequential colimit. And here you have this formula. Well, here it looks different because it's an inverse limit. But what's actually happening here is that this inverse limit is what you just see as at the first term, and then all the maps after that are isomorphisms. So this this is just the first iteration of f of x, f of m in this setting. So I don't know. So it's fun to use this formalism to understand left adjoints. Maybe I should also say that this situation occurs. So e.g., if A is idempotent. Yeah. So that's what's going on there. I'm sorry?
But it feels that in 2 and 3 you are idempotent.
In 2, no, not in 2. So this is not idempotent.
Ah, okay, so this is why you are, okay.
Yeah, so...
But if you took the completion...
No, it wouldn't, no. Yeah, in solid it would be, but then you'd be doing something else. You wouldn't be doing the algebraic inverting f, you'd be doing the other thing, yeah. So yeah. Okay, I went a little over time, I apologize for that. Thank you and see you next week.